Testing. 1, 2, 3.
Testing. 1, 2, 3. Testing.
Assalamualaikum and good afternoon.
Good afternoon, sir.
I already upload the notes in the e-learning, and you should take the attendance first in the forum. Can you see the PowerPoint? Can you see the PowerPoint?
Nampak tapi sebelah, sir.
How about now?
Okay. Clear.
Okay, the notes for this week is quite a few. Only a few. Lesser than last week. But the most important thing, there are so many exercises you have to do on your own. I don't want to waste time ask you to submit here today. But if we finish the notes this today, maybe you can do the exercise on next Monday. See lah how to push today. Alright. This week we talk about finite state machine synthesis. When we let's see from the beginning the definition of counters. Why we talk about counters? It is one of the common finite state machine happen in digital circuit. Either you design in FPGA or you design on VLSI, doesn't matter. If we think carefully from our past experience, because I think you have done this in electronic digit, even though you don't follow exactly either it is more model or Mealy model, whatever it is, as long as it is a counter, it must start from a particular state. Not necessarily you must start from 0. Some counter may start from 10 and then goes down to 9 and so on. Okay. A counter goes through fixed sequence of states. Doesn't matter, go up or go down, but it must go through a fixed sequence of states. And a counter should return to initial state. even though this is some exception, some counters, once it reach to the maximum, or we call it peak state, because some counters the peak state is the minimum. So it will stay there. Okay, it will stay there, doesn't move anymore until there is an initialization input signal. Somebody trigger it to go back to the initial state. And counters normally can also repeat indefinitely. Normally, okay. There are special cases where this is not true. Certain counters only just one loop. This is normally occur when we do system initialization. Only one pass or one loop. Then that's it. Then the main counters will take over the counting process. Alright. On the right side is from a system developer. Okay, because this is from experience. After you encounter various type of counters you design for many systems, you will see from the general definition there are certain exceptions, like I said before. Okay, you read on your own there. If you are being asked in exam, you of course you give on the left side. On the right side is mine. Okay. Because in the future you might take other class, so most lecturers accept on the left side because most of them have never done any industry job, or they have done on their PhD but not much lah. Okay, some lecturers are good. They went to the industry and do some attachment work there, take the challenge. I've done that after I did my master. I attached to MIMOS for almost a year. So you learn more when you do more. That's it. Okay, you cannot simply read books and expect to know more. All right, let's see. Most counters, but not all, are Medvedev state machine. For me, this is not true. Okay, this is not true. Normally, counters should have at least one output pin. But to know whether this is true or not, you have to read more lah. Okay, because the definition of Medvedev machine have no output logic. But if you have no output logic, then what is the counter for? Because the only useful thing in any finite state machine is the output pin. So why bother to build a finite state machine if you don't have anything to use? Isn't it weird? Okay. But look carefully the definition of Medvedev machine. There is no output logic, but the register output is the system output. That's what it means by Medvedev machine. It doesn't have what it means here. It doesn't have the combinational output logic. Remember the more model we have the next state combinational logic. We have the memory or register. We have the output logic, output combinational logic. Okay, so in Medvedev we don't have output combinational logic. We straight away take from the present state, which is also actually the output. Okay, so simply the output logic is just wires. Right. Most counters are single mode counters. It's not really that important for me, but not most, but we can define a single mode counters as no input. Is it true? No input. Let's think. If you are using a microprocessor or a CPU, you have a program counter, which is basically a single mode counters. Okay. But program counter in a CPU is not a single mode counters, because in a more complex CPU you can have address register. You can have loops. If you want to repeat the loops, you have to change the program counter register. So it is not a single mode counters anymore. So in a single mode counters, the counters will run on its own without external intervention. What does it mean here? That's why you don't need any input except, of course, the clock signal. In multi-mode counters, for example, program counters, you have to have input or several inputs to select the mode of operation. For example, certain counters in a PLC, you have the option to choose whether you want to count down or count up. So that's the purpose of the input, to select which mode you want it to run. Certain counters are being designed, it can jump to certain value based on certain input. Okay, you will see later on, hopefully. All right. Let's see a simple 2-bit binary counter. Very, very simple, okay? You can look in the state diagram below, because just a 2-bit, so to the power of n or to the power of 2, you can only have maximum 4 states. So if you start from state 0, using that assumption, you start from 0, you can see the arrow there, you can start the sequence from 0 and then you move up to 1, move up to 2, move up to 3, and then automatically restart at 0, and the process will continue, okay? Like as shown in the state diagram. It's a continuous process, and you see on the arcs there is no input at all, no label, either it's 1 or 0, no label, any input labels. Means that this is a no conditional as long as there is a clock. That's what the arrow tell. When a clock occur, it will change to the next state. Another clock occur, it will change to the next state, and so on. Okay. So let's see. Because this is 2-bit, let me label the present state as PS0 and PS1, as I showed you in the state table there on the right side. In your books, it is labeled as Q1 plus and Q0 plus. Okay, get used to it. We can put any label we want actually in the exam. It doesn't matter. Okay, you must know lah which one is for which. Normally we'll say lah this is a present state. So yeah, some lecturers like to confuse. They use different labels there down under the but definitely they will tell you which one is the present state, which one is the next state. Okay, now look at the present state column. We arrange first the states available 0, 0, 0, 1, 1, 0, 1, 1. This time, because there is no input, your present state is just that. You don't have pair like in the previous last week example. Okay, last week we have one input, so present state always occur twice, 0, 0, 0, 0. Why? Because when input 0 and when input 1. So this case, in this example, there is no such thing because there is no input. Okay, you list down all the possible present state first. Don't worry about the next step yet. Once you complete everything until 1, 1, then you got to think, what are the next steps? Okay, before that, this example use the maximum states available, okay? For the to the power of n, you have 4, but we use all 4 states. And as I told you last week, if we don't use any state, make sure you put it down here also. Don't leave any state. Don't leave any possible state. Okay. Now, how to get the next state? Look back at the state diagram. 0, 0, this the initial state. When clock happen, 0, 0 must go 0, 1. So now, on your next state, based on present state 0, 0, it must go 0, 1. Got it? Tidur semua.
Tak, sir.
Okay.
Yeah.
From 0, 1, if you look in the state diagram, we go to 1, 0. So in the state table 0, 1, we go to 1, 0. Alright? And so on. 1, 0, we go to 1, 1. 1, 1, we go to 0, 0. Alright. Now you have a complete state table. Based on Medvedev counter, or what we call it, Medvedev state machine, we don't need to worry about the output, okay? Because Medvedev, we just take out these present state pins as the output, so we just follow that lah. Now we already have the state table. Next step is to get the equation. So how to get the equation? Build the K-map. So that's your own exercise, okay? That's your own exercise. Make sure from this state table, draw the K-map. Can you get these two equations or not? And your output is based on present state only. So then, based on these two equations, build the circuit. It's your own exercise. Just draw on paper. Actually, it's faster. But if you are not sure whether this circuit what you have drawn is correct or not, only then you draw on quarters to software, run the simulation, see the sequence. Is it correct or not? I know. Some of you are lazy to do that. Only during exam you want to do the simulation. That's crazy. Okay. You are lucky you have a computer in front of you. So do the exercise on your own. And you cannot expect you do one, you know every design. So try do this on your own. Alright, let's see. Suppose we want to build a counter with arbitrary sequence. Can we do that? Okay. As we show here, down here on the left, if we have to the power of n and we use 2 bits, we can have all this kind of counters. It doesn't matter. We can also make counters doesn't follow any sequence. Looks like going up, but no. This one after 3 we go back to 1. After 1 we go back up, then go down again 0. And we can also have a state, a counter which doesn't use all the state. And as you can see here, state 2 is not used. State 2 is unused. It's still valid, don't worry. As long as you know to transfer from the sequence you plan, okay, either one of these 3 sequences we plan, to the state diagram here on the right side. This one is done for the last one. Last one. We start from 0, go to 1. From 1, we go to 3. From 3, we go to 0. Also valid. All right. Then from the state diagram, we build the state table. And you can see here immediately, we identify the present state which is not used. So the unused present state is marked by don't care. Okay, it's marked by don't care. Then after that we fill the rest of the next state, and then we and then we find the minimized equation. We are lucky in this this exercise because the don't care value, wait a second. Okay, it's unused. Looks like you can use this the next. No, you if you draw carefully a K-map. Let's see if I draw a K-map. How to draw a K-map here? How many? All right, 3 by 3. Where is it? Okay. Oh, my computer is so slow. That's why I hate to teach using online. I hope university can provide a new computer next semester. There are only 2 states, correct? So let's see what is the present state. PS1, PS1 slash PS0, correct? Yeah. That's weird. View ruler. Okay. Now I got a ruler. It's easier. Okay lah. All right. Because when you arrange in K-map, it become like this. Right? Now, identify which one is unused. The 1, 0. 1 and 0. So it should be here, unused. Wait a second. We need 2 K-map, correct? Let's me copy another next step. So assuming this is for on the left is P for NS1, on the right is NS0. So 0, 0 is 0, 0, 1 is 1, 1, 1 is 0. You can see here we cannot group 1, 0 output and 0, 1 output together, isn't it? Because they are diagonal. So we cannot group them together. So just stand on its own as shown in the table above. Mana pula? Itu dia. Alright. And for NS0, 0, 0 is 1, 0, 1 is 1 also, 1, 0 is don't care, 1, 1 is 0. So based on this, when we group them together, we can only group these 2. Okay. So that's why you cannot, in the step table, you cannot see the answer correctly. Okay, that's why you have to build the K-map. All right. Now, once you get the equation, you should be able to build the circuit. This is your electronic digit skill. Okay, very easy. All right. I better save different file. Susahnya. Dah lah, slow. Alright. Okay, now let's see multimode counters. A counter whose sequence in the book is the one that I strike out. When you give anybody a definition, don't repeat the word that people ask for. That's bad English, okay? A counter whose sequence depends not only on the clock, but also on some other control or inputs or signal. Okay, that's why I strike out the counting word. All right, example, count up, count down, blah, 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 blah. Not interesting. Let's see, this is a 3-bit up-down counter. Horrible. Why horrible? Because you need an input to decide the direction. So now it means your KMAT is 4-input KMAT. 4-input KMAT is quite big, isn't it? Okay. But in exam, they may even ask you 5-input. But I don't recommend lah. Never mind, let's see this. And because we have an input to determine the direction, that's why you see in the state table, every present state is repeated twice. Okay. For example, present state 0, 0, 0. When input is 0, the next state is 1, 1, 1. But when input is 1, it will count up. Then the next state is 0, 0, 1. And then you fill in until the rest lah. All these are based on your state diagram. But sometimes, even though it looks horrible, but because it's a very natural movement, it's a very natural sequence. Count up, count down. So it actually is easy. You shouldn't make mistake lah. Senang cerita. It's a free question actually. It's easy. The hard part is from this state diagram, how to do the K-map lah. You have to be careful. Okay. From the K-map, you should get this equation. I don't want to waste time to show you how. Do it on your own. If you don't get this equation, something is wrong with your K-map skill. So better repeat until you get it. All right. As you can see here, the equations, the Q0 is very simple, isn't it? Just based on one input or one feedback input. Very simple. Q1 is quite complicated, but Q2 is the worst lah. So you can repeat this example. Scientists think, how can we reduce this complexity of the next state? Okay, you can try repeat this example by trying to change from D flip-flop to JK or T flip-flop. You will see something surprising. Okay, look at the excitation table on last week notes. So replace the next state value. If JK, your next state should have two groups. Okay, you should have one group of Q0, Q1, Q2 as J, and then you have one group of Q0, Q1, Q2 as K. Two groups. For T flip-flop, this remain the same as this, but the sequence of the next state is not the same like in the D flip-flop. It's different. Okay, you can see on your own. That's one way to reduce the complexity of the next state equation. Okay, So if you look at the list there, we can implement this using logic gates, which is complicated. If you look there at the top. Second way, of course, like I told you just now, use JK or T flip-flop. Second method, you can use multiplexer. This one is interesting. It's very fast development cycle. Why? Because from this state table, you can straight away use the multiplexer. For example, in this problem, there are 16 states, correct? Because we have 4 inputs, actually. We have we have Q0, Q1, Q2, so 4 inputs. So to the power of 4, you get 16. 16 states. So you should use 16 to 1 multiplexer. 16 to 1 multiplexer. All right. So how are you going to use it? Wait, haven't complete yet. You must use 16 to 1 multiplexer. 3 units of 16 to 1 multiplexer. Why? Why 3 units? Because 1 unit for Q2, 1 unit for Q1, 1 unit for Q0. I think there will be one example there later on. So your development cycle is very fast because you don't need to do the K-map. You don't waste time do the K-map. As your state table getting larger, it's easier to do mistake, isn't it, in K-map? But if you transfer this state table directly using multiplexer, it's hard to do mistake unless you are really lousy. Ngantuk ke tak sihat, lain cerita lah. Okay, it's hard to do mistake, especially Q2 lah. Q2 here, you look, it is next to the border of the inputs, so cannot make mistake. All right. Decoder we use as a combination, not combination. We use decoder normally at the output. But for Medvedev finite state machine, you don't have combinational logic at the output block, so we don't use lah. But for other than that, if you have any combinational logic at the output, use decoder. Very fast. Okay. Not only just for development, these two MSI device, the multiplexer and decoder, why is my favorite when I use schematic entry? Because after I have done the circuit, I compile and then I simulate. If I found any error, I can quickly make modification. Means that I double check the state table. If there is no error with the state table, I double check from state table to the multiplexer implementation. Is there any 1 or 2 small error? Normally, if simulation is wrong, there will be 1 or 2 small errors. So it's very quickly you can check your work. Unlike the equation at the top there, it's quite difficult to get the equation, and then you want to double check, triple check the equation again. Oh man, I don't do that. Okay. But in multiplexer and decoder implementation, there are many ways. Okay. Because even though unused internal midterm is there already. Okay, you don't use. But sometimes, like I said in the early, when we want to build a finite state machine, the most important thing to consider is this the first prototype. If it is the first prototype, time is the most important thing. So use multiplexer and decoder. You can use this technique when you build your group assignment later on. Okay. Another method is to use ROM to replace the conventional logic, either at the next state or at the output. Yeah, you can, but it's really expensive. I don't advise this unless you want to build a very fast circuit. The trade-off is, what do you want? Do you want a small circuit but takes weeks to complete, or you want the work to be done in 1 or 2 days but large circuit? You have to think. So For ROM, of course, there are more ways lah. Okay, because you want to do storage there, so it's not feasible lah actually. But there are a few cases people do it. For example, in a lookup table, if your finite state machine is being used to generate a lookup table output, actually it's faster to build using ROM. All right, another method to quickly realize the circuit is to do behavioral Verilog. Okay, but be careful. When you learn Verilog, you will learn also all the technique above. You can use the Verilog to build the finite state machine using logic gates. You can use multiplexer or you can use decoder. But those is what we call synthesizable circuit. Synthesizable means you can have the physical circuit either on VLSI or FPGA. Okay, because some FPGA compiler, if it is a behavioral Verilog, you definitely cannot synthesize it on the physical FPGA. So you cannot test on the hardware lah, senang cerita. Okay, so you have to be careful. If you want to know more, take that class lah, CAD and ASIC design. If you want to work in Intel, or some of you might want to work in Singapore, where the salary is 3 times higher than Intel, take that class. Really take that class. Okay, especially this MCO will become a norm in our society. You want to work away, or sometimes you cannot go to the office or to the lab to do your work. You have to do the work in your house. But if you are an IC designer, this is the happy time for you. Why? Because this is exactly what you do in the lab or in the department of the company. Some department in Intel using exactly Altera Quartus 2. Because especially after Intel bought Altera, okay? What you do now at home or in your hostel or anywhere, all you need is a notebook and internet line. And you do the work on your own. So this is the happiest time, because especially those who have child already, or if you are girls, this is a very good career for you, because you can do your work at home. All right, let's see. Okay, this one is a very common or topical discussion in any digital system class all over the world. Sequence detectors. This is a very important actually, especially for those who may work in automation industry, automation, control, robotics, or nowadays a new era has been made if you want to work in automotive. Okay, automotive also nowadays are using FPGA. I don't know Proton has started use it or not, but since Geely already bought over Proton, I think they may use also FPGA in the next 5 or 6 years. If they still don't use, then don't know lah, still a Proton. Okay, companies especially like Tesla, they are using FPGA to build their ECU, electronic central unit. They don't have CPU, they have ECU, electronic central unit. And at the same time, Tesla is electric car, so the main controller is no longer dependent on the CPU. They don't use Pentium or AMD, the one throw away lah. They use FPGA as the main controller. So that's why in US, if you look at job vacancy, okay, if you look in ads, job vacancy, if you are connected to anybody in LinkedIn, job vacancy, try join FPGA groups. Wow, man. In US, UK, really huge opportunity. This is the time for you to make money lah. The only thing that you have to leave there lah. Okay. All right. What is a sequence detector? Sequence detector. Macam mana nak cakap? First, I think I need to define first what is a sequence detector. Okay, like this. Let's see the example first. We have a series of input where we need to detect and analyze and then determine whether the input sequence occur or not. Okay. In this example, we want to detect a sequence of 110. 110. Every time sequence 110 occur, high to indicate the sequence occur. So that's why you see at the output row, you see 1. When input at the top 110 occur, you will see output 1. And then you go ahead, the input 00110 occur, output occur high again. Then input go again 11110 means we detect another 110. Okay, that is a sequence detector. The sequence can be anything. Okay, in exam, of course, we try to limit the sequence to 3 or 4 sequences only. Depends. But this is always like this. But this one quite easy. There are more complex sequence. For example, if your sequence that you want to detect is 010 or 101, then you will get more headache. That one later on we discuss. But this is what we mean by sequence detector. Okay. So how are we going to build a sequence detector? Let's see the previous note. We start with the expected main sequence. Okay. If you look in the example, the main expected sequence is 110. This is the first part of the state diagram that you need to draw first. 110. Okay. 110. Main input sequence is 1 1 0. Get it? You always start your initial state at 0. Okay, it's normal because we know the easiest method is when you power on, all flip-flop are 0, so you start at 0. But what we interested actually at the input, so that's why you see here the arcs are 1 1 0. That is your main sequence. All right, let's see. Second, assert the output at the last state. Okay, in the example there, you can see the output of last state is high. Third, add exit up to cover all possible transition. Okay, means that the last arc after you reach the last state, where should it go? It not necessarily like counter, you must go to the first state or the initial state. No, not necessarily. You must find the best place to go to restart. Okay, and then you have the last thing you need to do is complete all the state arcs. You must have a pair of exit conditional arrow. You must have a pair. If your input is 1 only, it must be a pair. If your input is 2 bits, you must have 2 pairs, and so on. If you don't have any condition, it means that it will go to that state, you must have an unconditional arrow. All right, let's see whether we can finish this main sequence. Okay. So now you see the output is 1. Your state symbol is S3. Okay, now you have to ask yourself, where does this S3 should go whenever we whenever we get either input 0 or input 1. To know this, what you can do is look at the example in the sequence trend there at the top. So after you detect 110, if your input is 0, your output is 0. So that means your S3 should go to S0. Let's see another example. If your sequence detect here 1, so the next input is 1. Okay, the next input is 1. If you look carefully, it is as if you already detected the first sequence of 110, correct? So you cannot go back to S0. You should go back to S1. All right, let's see. All right, you assert the output last. Okay. Hilang. That's number 3. Okay, where you want to go back? So, nyemak betul lah Telegram ni. Sekejap. Let me... Mana aku nak buat? Let me disable Telegram. Kacau screen saya lah. Let me kill the program. So if you want to say, you want to give message, you can use chat in the meeting. Okay, see there, S3 go back to 0 because of the first sequence we detect. If the input after that input is 0, means you don't detect a sequence yet. Again, okay, so you will get output 0. So that's why we repeat at S0. But on the second output here, after we detect output sequence 110, if the input is 1, we go to S1 because we already accept one part of the input of the sequence. Okay. So now let's see how to complete the rest. How to complete, because you look, battery pula. Okay. Okay, now if you can do this, you already got 67% of the state diagram. That's a lot, 67%, you already got B. Okay, so now the last part is to carefully complete all the arcs, okay? Because you see at S0, the output arc is not complete. You only have output arc when it is 1. But what happens when output arc is 0? Look at S1. You only have an output arc when it is 1. There is no output arc when it is 0. S2, you only have output arc when it is 0. There is no output arc when it is 1. But S3, we already completed it when we want to check the initialization of the sequence. Okay, so the only state is complete is S3. So how to complete S0, S1, and S2 arc? Okay. All right. No pair for unconditional arc. The only thing you don't need to is no pair for unconditional arc. I don't think it has here. Let's see. So what happened if the input is 0? At S0, we stay at S0. Why? Because we haven't found any component of the sequence. Okay, that's why we stay at S0. And at S1, if we get the input as 0, we restart at S0. Why? Why we need to restart? Because whatever input 1 we found is not valid anymore. okay, it's not valid anymore. For example, if you find a sequence 1, 0, 1, 1, 0, 1, 1, 0. So the first one is no longer valid. That's why when it's 0, you have to go back to S0. Now, here at S2, when the input is 0, you find the sequence. You flag 1 lah, you go to S3. But if the input is 1, what you do? You stay at S2. This one, because of this example, look here. If you, after 1, 1, 0, if you find 1, you stay, wait there. If you find 1, it's fine, you go to S1. But if you find the next 1, you stay at S2. But if you still find another one, you stay at S2 here. Here also S2. Only then when you find 0, you go to S3. Okay, you see this one? You get 1, you get 1. If it is another one, you stay at S2 until you get 0. If you don't get, you don't get lah, forever lah. Stuck there, no choice. Okay, all right. So this is your complete state diagram. So from this state diagram, you know we have 4 states. So list out the present state first, 0, 0, 0, 1, 1, 1, 1, 0. Here I'm using gray coding, okay? Gray coding. And then because it has an input, that's why I wrote 2 rows of the same present state, because based on the input will affect differently. All right. Now the next state, look at the arrow. When present state is 0, you are at S0. When input is 0, you stay at S0. So and S1 and S0 are 0. But when input is 1, you go to S1. S1 is 0, 1. S1 is 0, 1. So when present state is 0, 1, you look at the state diagram, 0, 1 is S1. When input is 0, you go back to 0, 0. So that's why your next state is 0, 0. But when your input is 1, you go to S2. Your S2 is 1, 1. Okay? 1, 1. Now, when you are at S2, which is 1, 1, if your input is 0, you stay at, you detect already. So you go to S3, which is 1, 0. If your input is 1, you stay at S2, which is 1, 1. Now, when you at the end of the state, which is S3, 1, 0, if input is 0, you go back to S0. If input is 1, you go back to S1, which is 0, 1. So your output column has only one output, which is when you are at state 1, 0. Okay, got it? Maybe you need to try this on your own without looking at the answer. All right. So based on the state table, we draw the K-map and then find out the equation and then build the circuit. All right. Do this, draw on your circuit on your own. You can use the quanters too to confirm whether it's correct or not. Here's the answer. What else? Yeah, that's it. This is why. This is if you look in the equation, the NS0 is simple, isn't it? Only depends on in. While NS1 is complicated. You must have 2 AND gate, 1 OR gate. So that's why you see the complicated here. But if the same state diagram you use binary encoding, salah topik ni. This is gray coding, isn't it? This is gray encoding. This is binary encoding. So in binary encoding, your next state is a little bit more complicated. Just imagine if we are using 3 or 4 flip-flop, the next state combination can be very, very complicated. That's why we use gray encoding. All right. How can we do this if we want to use Mealy model? Okay. Actually, you can do two ways how to get the Mealy model. You can reanalyze the input-output sequence and build the circuit, build the state diagram, or if you already have the Moore model state diagram, you can analyze the Moore model state diagram and convert into Mealy model state diagram. All right. For me, normally I do that way lah. Seldom for me I analyze straight from the input-output and build the Mealy model. Seldom. I have done that before, but I have miserable life to do that. So that's why after that I prefer from Moore model state diagram, I convert to Mealy model. Okay, if you look at do we have this? Okay. On the left side is the diagram. If you take the notes last week, one of the rule I gave you to convert from Moore model to Mealy model is to eliminate the state where the output is available, correct? So in this example, the output is only at S3. So eliminate S3. Now the problem is when you eliminate S3, where does the input should go? The arc. Where does the arc should go? That's a good question. Look here. Normally at S0, S1, S2, they are the same. If you look carefully. Remember, in Mealy, input, output, input, output. So 1, 0, 1, 0, because the arrow, the arc is 1. The S1 to S2, the arc is also 1. That's why you get 1/0. Here also 1/0. Now the problem is here, S2. This some kind of art to determine where it should go. But you can analyze it logically, okay? You can analyze it logically. If you have to look in sequence. When you have an input 0 here, you should detect the output, correct? But you want to know, after you detect input 0, what is the next input you will detect? Here, if you look at the Moore model, if you detect another 0 here, you should restart at S0, correct? You will restart at S0. But if you detect 1, you should restart at S1. Okay. So let's see. It should be here. If 0, 0, you should get 1, but you detect 0, but you detect the sequence, you deflect output 1. But then the next thing is next is you detect 0. So that's why here S2, if you look here carefully, S2, we go back to S0 when we detect input 0. It's the same as from S3 to S0, correct? But because from S2 to S3 is considered we get output 1, that's why now the output is labeled as 1. Got it? You don't get it?
Kurang also.
Sekejap. I think something wrong lah dengan diagram ni. What is wrong? Siapa yang buat diagram ni? This is wrong. If we look at the Moore model, S2 will go back to S1. Oh yalah, betul lah. Betul. Okay. Alright. S2, if we detect another input 0, we'll get an output. Yeah. But now we eliminate S3. Correct? Alright. Now let's see what is the next input. It can be either 0 or 1. Okay. If it is 0, we should go back to S0. That's all you need to do for the time being. You draw S2 to S0. Wait a second. Saya punya model ke yang salah? Betul juga. Ya, boleh. Dua-dua boleh. Okay. S2 go to S3, but now S3 is eliminated. But S2 will go to S0 if the next input is 0. That's why here S2 straight away go to S0 in the Mealy model, because the next detected input is 0. Means that you have to restart all over again, like in Moore model. When you find out input 0, you have to restart. But where are you going to restart? Is it S0 or S1, as we see in the Moore model, in the Mealy model? In the Moore model, okay? We have to always answer, where should we start? Is it S0 or S1 in this example? So that's why if we know the next input is 0, it will restart at S0. We follow the Moore model. Why? Because at S0, there is an arc that will stay at S0 if the next input is 0. Okay. Where this also means your input sequence is complete. You start from S0, your input arc is 0. So 1, 1, 0. So that means while you transit from S2 to S0, your output is completed. That's why we label S1. Because we fulfill. If you look in the Moore model, 1 from S0 to S1 is 1, S1, S2 is 1, S2, S3 is 0, 1, 1, 0. Then you should give an output at S3. Correct? So in Mealy, you must follow the same sequence, 1, 1, 0. So if in Mealy, 1, 1, and then in S2, 0 to S0. So that's why you have to give an output here.
So maksudnya tak ada yang balik ke S1 rasa kan? Dari S2 tak ada balik S1.
That's a good question. Why we didn't go back to S1? If we look in the Moore model, we can only go back to S1 if the next input is 1 after we detect the output. So here in the Mealy model at S2, actually you have two options. Somehow this sequence you can get two options. You can stay at S2 or you can go back to S1 in your Mealy model. Both is acceptable. Both are acceptable, okay? Why? Somehow because of this. If you look in the Moore model at S2, there is a feedback input here, 1. So that's why in Mealy you can also do that. If this is not available, then in Mealy, S2 must go back to S1. And there is no output. There shouldn't be an output. Because you don't detect 110. You detect 111. But let's analyze it logically. Which one is more accurate? Is it go back to S2 or go back to S1? Okay. Let's assume now your sequence is 1110. You should detect a sequence, correct? The only thing is you have 3 ones before you get a 0. So let's see in the Mealy model. 1 from S0 to S1, another one S1 to S2, and then you stay at S2 because you find another one. And then you get 0. So you go to S0. And then you give a flag of the output lah to high. What if your Mealy model here, the arc, you go back to S1. Instead of you draw this, you go back to S2 and it is 1. You draw, you try to follow in Mealy model, S2 go back to S1. So 1110 will become 1 from S0 to S1, and then S1 to S2, another 1. And then the third one, because you draw from S2 to S1, so you will go back S2, go back to S1. Then your input is 0. You go back to S0. From S1, you go back to S0 without flagging that you detect already a sequence. See? Looks like the same, isn't it? But when we analyze it properly, it's not the same. It's not the same. So here in more model, it's okay. You can go back here. Let's see in more model. 1, 1, 1. You stay at S2, and then you get 0. You detect in more model. But in Mealy model, somehow if you want to copy exactly the same here, you cannot find it. So you have to careful this. I cannot give you any rules to do about it. You have to reanalyze after you draw the Mealy model. If you feel headache, it's okay. Never mind. Tomorrow, tulat, you look again. Okay. All right.
Okay, sir.
So let's see. From the Mealy state diagram, you build the state table, normal procedure. This one we use also the gray encoding. Okay, gray encoding. Now we only use S0, S1, S2. So the last one should be don't care. Why now it is throw as? Oh, this is wrong. Ini macam sama more model punya state table lah. Maybe saya salah copy kot. Tengok dalam buku awak. Dalam buku awak sepatutnya this if you look at the number of state sepatutnya ada 3. So your present state at 10 because this is encoding 10 lah yang tak guna. So 10 should be marked in the next state as don't care, don't care, don't care. So your output should depends at present state. Maybe I should correct now lah. Tak boleh, awak tak nampak. Okay. Where is it? Okay, found it. Apa, Abang Amir tak buka? Meh. Tak apalah. Yalah, saya rasa saya salah copy lah. Okay, should be like this. Now the output should be this. Based on the Mealy model, when you are at S2, when input is 1, your output is 0. So this one you should label as 0. When your input is 0, then it is 1. Careful, because you are now at Mealy, so every output must have, you have to analyze for both inputs condition. You have to do like this, 0, 0. Then here also you have to do like this, 0, 0. Okay. You get it? Boleh tak? Because remember in Mealy model, your output depends on present state and input. That's why your output must be analyzed for both inputs, input 0 and input 1. Alright? So let's see your, this one implement using marks. Okay, never mind. Forget for a while. Okay. So the only difference here, if you look, this in Mealy model, you only save one state. So from 4 states, become 3 states. Looks like as if it doesn't worth it lah, because come on lah, you still used to flip-flop, correct? But for exam purpose, test purpose, sometimes we need to ask like this, no choice lah. So you need to brush up lah this skill. So now, if you want to speed up the implementation, we can use multiplexer. So 2 multiplexer is needed. The multiplexer, this is wrong. This is wrong. Can you do it on your own for the time being while I repair the notes? Try to implement this. If we look at one go, you should use 8 to 1 multiplexer, correct? Because you have present state 2 bits and you have an input. So you have 2 to the power of 3, 8 lah. So you should use 8 to 1 multiplexer. And you need 2 of them. You need 8 to 1 multiplexer at Q1 and you need another 8 to 1 multiplexer at Q0. But I think that's what the notes want. It is membazir lah sikit. We try to optimize. Can we reduce 8 to 1 multiplexer to become only 4 to 1 multiplexer? Can we do that or not? Okay. So the easiest way to do that is to eliminate X, the input. So try to do that on your own. Use only 4 to 1 marks. Alright, I completed the correction. Look here. To make it easier, the the table, I changed to input-output. So that is easier lah for you to see. For PS0, PS1 is connected to the input. So the input is represented by the state S0, S1, S2, S3. And on the right side of the table, you see it is the output or the Q1 plus, Q1 plus or Q0 plus at the bottom table. So now we know S3 is not used. So we have to put don't care. Now we have a confusion. Why? Because in the input is labeled as X. That's why I don't like to use that label as an input, because you will confuse with don't care. So let's change it into in, or you can use any other label if you want to. So if the input here is in, now when at present state 0, 0, when input is 0, 1, Q1 plus is 0. So it doesn't matter lah what happened to X. So it always 0. So that's why here at S0 we put 0. Okay. Now when present state is 0, 1, the Q1 plus is 0, 1. So it follows input in 0, 1. So might as well label it as in. So that's why in S1 I label it as in. Let's see S2. S2 here is 1, 1, correct? Because we are using gray encoding. So 1, 1. So Q1 plus is always 1. So it doesn't matter what happened to X, it always 1. So that's why here at S2 it is always 1. So there goes your Q1 plus, or here I put label as an S1. Alright, then we repeat the process in Q0 plus. Q0 plus is more easier because if you look Q0 plus, when present state is 0, 0 or S0, Q0 plus follow input 0, 1 also. So you will label as in. When present state is 0, 1, Q0 plus also follow in. When present state is 1, 1, Q0 plus also follow in. So that's why I label all of them as in. And S3 is don't care lah because we don't use it. So there goes your multiplier. Very easy. Alright. Let's go for more complicated. I think cukup lah hari ni kot. Korang semua dah pening kepala. You do your own exercise. I don't want to tell you what exercise you should do. You want to learn, you do your exercise. Be responsible to do what you have to do to learn. Because later when you work, you cannot expect your senior engineer to show you everything. You have to do on your own. Alright. So try do the exercise on your own. If you don't understand or any confusion arise, write down on a paper so that on Monday when we have another class, you can ask me during the class. Okay?
Okay, sir.
Any question before we end this session?
Sir, untuk assignment ada ni tak? Guideline tu. Kita orang hantar proposal. Contoh.
The simplest example you can see is the serial multiplier. The only difference is if we have the hardware, I believe the lecturer told me there are a few stock already arrived in the lab, the CPLD. But the problem is, I don't think any electronic shop is open for you to buy 7 segments, switches, and so on. So whether you have the time or not to build the hardware. But let's assume you are going to interface with hardware, the serial multiplier. You should have 7 segments, 4 units, correct? In fact, yeah, you need 4 units also. You can swap or you can scroll to show multiplier, multiplicand. But then you need result 8 bit, isn't it? 4 by 4, 4 times 4, you should have 8 bit output, correct? So, but if you have only 7 segment, you can still show 8 bit result. How? Anybody can give idea? Show everything in hexadecimal, the result. Input you can show in binary is easier lah for you to see what's going on if you show the input in binary, but you can convert into hexadecimal at the output. So serial multiplier is a very good example of exercise. Why? Because you have several type of register there. You have parallel load, the input multiplicand, multiplier, and then you have shift register. The multiplier you need to shift. Remember, you have to shift 1 bit at a time, 1 cycle at a time. And then the result must be stored. After the accumulator, and at the same time, the result should be able to be shift 1 bit at a time. So that's why it's a very good example of the designer. And the control unit. What control unit do you need? If you look at the analysis in notes week 7 or 6, I don't remember. We must be able to control the data path in such a way that first we add, then we load, and then we shift. And you repeat this process 4 times. So your control unit should have the main control unit that produce the sequence, and then another control unit to count how many loop you have done. Okay, some people combine these two in one finite state machine. But what happens if you want to expand into 8 times 8 multiplier? That's crazy. You have to redo the finite state machine. If you split them, the counter is the only thing that you adjust. That's why it's always good to split control unit into several components. Okay. So serial multiplier is a good exercise because even if you build a simple circuit, for example, when I did my master, the filters, I use serial multiplier to multiply the filter. Of course, I need lookup table and so on. But the simplest part in the filter is to do the accumulator, multiply, accumulate, multiply, accumulate, multiply, accumulate. You will learn about filter in digital signal processing class. I don't know for you SKEE and SKEM nowadays. When do you learn that subject? Is it 3rd year or 4th year? I don't know. But it's a very, very good subject, digital signal processing. Nowadays, nobody can run for it if you want to get rich lah. If you want low salary, never mind lah. No need. So you have to come out with your own idea lah. You want to build maybe an aircon unit, but or washing machine, or you want to build I don't know, traffic light, but I don't really like traffic light because one, you have done that in your digital lab. Second, it doesn't really have separation of control unit and data path unit, so you don't really learn about it. So your requirement for the group exercise is you must have a control unit and a data path unit. That's one. In your data path unit, you must have different type of register. That requirement number 2. Requirement number 3, you must have operators. In serial multiplier, your operator is your adder. Okay. Some design, you might have to use comparator. That's an operator also. Okay. That's why you have to write a proposal. You have to plan a block diagram to show how your data path unit should be, how your control unit should be, especially the data path unit. What are the components that you are going to use? Because you are especially register, you are going to use a lot, isn't it? Because when you want to display on 7 segment, you have to store the data in a register first. You cannot simply straight away from the output of the multiplier and then you display on the 7 segment. No, it's not that simple. Maybe you need another processor, your BCD, if you want to show the result in BCD lah, in decimal, okay, in decimal point. Alright. What else requirement? If you analyze the serial multiplier, what else the requirement that you need? You definitely need a switch, a set of switches to input the multiplier, to input the multiplicand. Okay, you need switches. And maybe last of thing you need, an LED to indicate that the calculation is completed. The LED can be as a flag to show that it is done. Or maybe you have some other ways to show that the output is ready to be used. Okay, any other question? Maybe later I will make a spreadsheet so that you can put your group's name. Have I done that? Not yet, isn't it? I will make a spreadsheet. You write down your group's name. What is the title of the project? Of course, then you have to submit to me your proposal. You have to do the proposal quickly in 1 week. If not, you don't have much time to do the rest of the project. What else? Because I don't think we are going to have a face-to-face presentation. You have to think, how are you going to do the presentation to me? I definitely want to see your work. If it is a purely simulation, maybe like this, we use Google Meet to present your work. But for FPGA work, I don't really like only simulation. From my experience, when you do only simulation, impossible. First simulation, when you burn on the hardware, it works. Impossible. I'm going to tell you a bad story a bit here, because I saw lecturers from other university present at international conference, bullshitting. They build design using Altera quarters, but they never test it on FPGA. And then they claim they do this, they do that, they do this. And they spend 4 millions of people money to do the project. Saya nak baling kasut je masa tu. Very arrogant punya lecturer. But when I think there are many foreigner in that rooms, I don't want to argue with stupid people. Even though that guy is professor. Bullshitting, I know when people bullshit. Because I am the one who first graduated in Malaysia using FPGA. So I know when people bullshit. When I did my master, my work is not just on simulation. I have to make sure it works on the hardware. Like I told you in the class, isn't it? My JPEG decoder, first we read the data from hard disk, we decode, we uncompress or decode, and then I send to my display controller, and then we display it on monitor or CRT. Everything on FPGA, not even a Pentium CPU being used. So it's difficult sometimes to work with people when you know everything and then you know people bullshitting you and bullshitting other people. But that's life. You will see later on when you work, especially you work in multinational. They are seriously, they are very professional people. You bullshit one time, they keep quiet. You bullshit the second time, they might discuss with among themselves with their bosses or among managers. Third time you screw up, you are fired. Some manager don't give you any chance. If you are stupid, you don't know, you just say you don't know. or maybe you are bogged down with some other work, so that's why you haven't finished the assignment given to you. Just say you don't have the time yet to complete your task, but don't bullshit. Because my master student now in Altera department in Penang, most of them now are doing two jobs or two design at the same time. Two design at the same time. Just imagine you do two master work at the same time. They have to, because there are no people. It's very difficult to get engineers who can really design FPGA. Okay, that's how difficult they are. But of course they get bonuses because they do more work. So it's up to you. You want to learn, you do. Okay, you want to cheat to me. Sometimes I'm very busy. I'm not well. I let students go cheating. They are not cheating me actually. They're cheating themselves. One day you will get caught on your own. At that time you cry also. No use No use. Okay, I think that's all. It's 4 o'clock already. You can message me anytime. Don't worry. All it takes is your time and your effort. You want to learn, you do it. I know now it's tougher because of the MCO. I also myself have tough time to do. There are many things I have to do, but I don't have the motivation to do because I MCO. But life has to go on. We have to do what we have to do, what we can do. All right, thanks all for coming, for presenting. Right, make sure you record your attendance in the forum. Just say hi. All right, thank you.
Thank you, sir.
Thank you, sir.
Thank you, sir.